last topic on this course, we're going to talk about differential equations. This will actually allow us to frame some of the things that we've talked about earlier in a slightly different format, including things like growth and decay as well as other processes. We will see the solutions to the very first simple differential equations, how to derive them, and what that might mean for your future Calculus 2 courses. So to start off with, let's give a definition of what is a differential equation. In terms of the equation itself, normally we think of things like x squared is equal to 4, and when we solve it, we produce a number answer, in this case, plus or minus 2. A differential equation is also an equation, but it relates not just a variable and numbers, rather it relates one or more derivatives of some function to the function itself. So in the differential equation, we will be seeing the function and its derivatives. Solving the differential equation, therefore, is not coming up with a number answer, but rather to come up with a function that satisfies the given relationship. Let's start off with probably the easiest function to take a derivative of, y equals e to the x. The question here asks to simply write a differential equation that involves this function. Well, I can take a derivative, and what am I going to get? The derivative of e to the x is just e to the x. And here we go. This in itself already is a differential equation. In order to write it more like the relationship between the derivative of a function and the function itself, I might also notice that this e to the x is my original function, which means that I can rewrite this expression as y prime is equal to y. This in fact, encapsulates how e to the x relates to its derivative. The derivative of e to the x is itself. This differential equation describes the behavior of this function and its derivative. Now, e to the x is a really nice function, so I can in fact extend this out even further. I know that the second derivative of this function will still just be itself. I also know that the second derivative will be the same as the first derivative, and I can come up with lots of differential equations that involve this particular function. All of these are what we call a differential equation. And once again, the solution to it is the function that satisfies it, not a number. Let's take a look and see if we are given a function and a differential equation. How can we determine whether or not this function, in fact, satisfies this differential equation? There are a number of ways to proceed. You can take a derivative and then you can plug in the function itself and see if the equality actually holds, or you can try to derive an equation and see if your derived equation matches the one provided. So let's start either way by taking the derivative of this function. So it's e to the power 3x, which means that the derivative is itself times the derivative of the inside. And then, of course, I notice that this e to the 3x is my original function, so I can replace this with my original function y, which will then give me that y prime is equal to y times 3, or 3 times y, which is exactly the equation given here. So yes, this function, in fact, satisfies this equation. So, in other words, this function is a solution to this differential equation. Now, this is the simplest differential equations and the nicest functions to work with, and we can generalize this result to something that involves not just a number 3, but a general constant k. So notice here that I have rewritten my equation in the dy by dt form, but I can also work with it in the y prime form. Y prime is equal to ky. What the result is saying is that the solutions to this equation are exactly the exponential functions, where k appears as the constant in the actual exponential, and this number c up in the front, being just a constant, can be about just about anything at all. Let's check to make sure, just like in the previous example, that this equation is in fact satisfied by these functions. So I'm going to take the derivative of my function here. Now, in taking the derivative, first of all, I notice that I have the constant c. By the constant multiple rule, I can leave it alone and then take the derivative of what's remaining. What's remaining is e to power kt, so the derivative is itself times the derivative of the inside, which is the power, so the derivative is going to be k. And then, of course, I noticed that this ce to power kt is the exact same as my original expression for my function. So this is, in fact, just equal to y. And yes, I get that y prime is equal to k times y, which is what this actual result states. What is actually a stronger result that we're not going to prove, these are the only solutions to this equation, which means that if I have a differential equation like this, the only functions that satisfy these are the functions of the exponential form. Okay? Nothing else will satisfy this differential equation. So 2 important notes to highlight once again. Solutions to differential equations are functions, not numbers. So you're after an actual function of certain form. And the solutions, of course, depend, being written in this format, will depend on the values of c and the values of k. And we will get a number of different scenarios occurring. So for example, and we've seen this before, if k is positive, so here the exponent is a positive number, or in a differential equation here, the rate of change is therefore positive. What we get is, of course, a positive or a growing, increasing exponential function, which means that generally we'll get exponential growth. What that means, for example, on the graph is if we sketch it, we get a function that we expect to increase and therefore look like this. This is when c is positive. What happens if c is negative? Now, this is not likely to happen in real-life applications, but for mathematical completeness, let's consider that case. If c is negative, I'm going to get the exponential function, but with a negative in front of it, which means that everything gets negated. So what I actually have is the graph that looks like this. Okay? What about the case when k is negative? Well, if k is negative, what I have here is the negative power in the exponent, which means I generally get exponential decay. And again, we can have 2 different cases for the various values of c. The positive value of c is the one that is a more familiar exponential decay that looks like this. And the negative value of c, once again, is not going to be a terribly useful property to have in the realistic applications. But again, just for mathematical completeness, I'm going to include this here. The collection of these curves, because we're getting really a whole collection, right? Depending on the value of c, I might have this, or this, or this, or that, or any other of the infinitely many possibilities. The collection of similar curves is called a family of curves. So in fact, what I have here is a family of solutions. Without specifying what c and k are, my solutions are an entire set of related and similarly shaped curves. If I would like to pick a specific member of this family, I need further information. In particular, if I have some kind of knowledge about the value of c, then if I have infinitely many of these related curves, just fixing one point will allow me to fix the one particular member of the family of solutions that I have to consider. The problems like that are what we call initial value problems, and that is when you have a particular value that is specified at some point. Generally, in real-life situations, you will have the value that is specified at 0, the starting point, so to speak, a real initial value, but this does not need to be the case. You could have a specified point that does not happen at t equals 0, but happens somewhere else, and the process will not actually change. The process of finding a solution will not actually change. Okay, so let's go through this one. What do we have here? We're asked to find the solution to this equation, which again I can rewrite in the prime form if it's a little bit easier on the eye. And I also know that I have this particular point that my solution has to actually contain. Now, in general, from the previous slide, what I know is that the solutions to the equation y equals ky are family of solutions of the form y equals ce to power kt. So let me record that here and then try to match to what I actually have. So the solutions to y prime equals ky are y is equal to c e to power kt. What I have here is I need a solution to y prime equals 5y. So what I immediately notice, of course, is that it means that in my case, k is simply equal to 5. So now, matching this to the solution provided is going to give me the fact that my solution is going to be c e to power 5t. Right? What I have here is k is equal to 5 in this case. Now, the nice thing about the differential equations is that you can always check to make sure whether or not you're doing your arithmetic or sort of this matching game correctly. You could take the derivative of this guy and make sure that it actually satisfies this equation once again. Now, what I have here is almost a perfectly good solution, except for I still don't know the value of c. This is where the initial value will come in handy. I'm going to plug this information into my equation and solve for c. So what am I going to have? My initial value says that at t equals 0, y is equal to 3. So y value itself is equal to 3, which will be the left-hand side here. And this is the case for when t is equal to 0. So that's going to go into my right-hand side. c e to power 5 times 0. 5 times 0 is just 0, so what I actually get from here is that 3 is simply equal to c, which means that overall my solution is y equals to 3, this would be my c, e to power 5t. And what of course you just noticed too is that whenever I plug in 0, this power will be 0, which means that this entire thing will be equal to 1. So I will always have that c is equal to the value at time equals 0, which is why in general we actually have a notation for it. In general, y of 0 is what we call y naught, the starting value, and then solution is, or can be written as, y equals y naught e to power k t. So instead of writing this c down, that might or might not be the actual value at 0, I know that if I have the value at 0, that is simply the constant in front of my equation. Look at our first application here, and that is the model for population growth. Generally, the size of a population depends on numerous processes. For our first model, we're going to make a bunch of simplifying assumptions so we can carry out our very first calculations. First of all, we're going to assume what we call system being closed, and that means that there's no immigration and then there's no emigration. So whatever happens to the population happens to the population sort of inside, very pandemic-like. We're also going to assume that birth rates are proportional to population size. So if my population is denoted by P, then I'm going to assume that the rate of births is equal to some constant b times the population size. So we're assuming some proportion of the population is actually giving births to other humans or other species, I suppose. We're going to assume something very similar about death rates. We're also going to assume that they are proportional to the population size. Again, this is our very first model, so it does have simplifying assumptions. More realistic population models will involve the fact that, for example, death rates are density dependent. The denser the population, the higher death rates actually are. Now, with these ones, if these are the only processes that affect the population, then we can fairly quickly think about what actually then happens to the rate of change of population as a whole. What affects it? Well, first of all, of course, the rate of change means that I have to account for positive changes, which is the rate of births. This is what adds to the population. And then I have to take away the negative changes, so the rate of deaths that happens in the population. Now, this entire equation is based on rates of, which means that this in itself is a differential equation. The rate of change of population is the derivative of the population with respect to time. The rate of births being proportional to the population size is just BP. The rate of deaths is dP, where B and D are some kind of birth and mortality constants. Now I can see that I can simplify this a little bit because I can actually factor P out on the right-hand side. So what I have is dP by dt is equal to B minus D times P. Or, again, if you prefer the prime notation, P prime equals to B minus D times P. You can already see how this is similar to the equation that we've just talked about of y prime equals ky, except for my constant k here is composed of two other constants. But this should not affect how I actually proceed to calculate the solution. Let's take a look at real Canadian population data. We're going to take census of 2000. We're going to build a model based on that information, and then we're going to predict the population for the current year based on our model. So I'm going to start with population size in 2000 being 30,689,000. So this is going to be my P of 0. Birth rate is 0.0106 per capita. We often see these as statistics, and per capita means that it actually is the birth rate. So this is exactly what our constant B from the previous slide is. The death rate, 0.0071 per capita, so on average per person, is again, because it's per person, it's already the rate of deaths. So this is our constant D. So altogether, from the model that we've just derived, we have that P prime is equal to B minus D times P. And now I can plug in real numbers for B and D into my function and see what happens. So what I'm going to have is P prime is equal to B minus D I'm going to do the arithmetic on the side here, and I'm going to get 0.0036 P. There are a couple of things to notice right away. For example, the fact that this number is positive, which means that the rate of change is positive. So that means the population is in fact growing. The other thing to notice, of course, is that this differential equation is exactly in the form of the equation whose solutions we've just discussed. That means that I can immediately come up with the solution to this equation. Y prime equals ky, remember, meant that the solution was y naught e to power kt. And so in a very similar manner, I will just match this equation to the corresponding solution in this format. So what that would mean is that the population size is then equal to the P naught e to power of the constant, so 0.0036 times t. Okay, so notice that this constant of mine here has now traveled into the exponent as k did on the previous slide from that equation. Now, of course, I also know the value for P naught here if I'm taking year 2000 to be my starting of the data collection year. So altogether, I have 30,689,000 times e to power 0.0036 t. Once I have an actual model, I can compute my prediction for any year using this model. So what is my prediction for 2020? Let's see what happens if I plug in. Now my countdown started year 2000, so 2020 will correspond to 20 years from then. If I plug in 20 into t and compute this number, what I am going to get as the approximate population is 32,980,098 people. Now, I'm not including decimal people because that's not a thing. So this is my approximation for the population based on the model from the Census 2000 data. Now, we can, of course, look up Canadian current population. In fact, there's a really handy real-time model that runs on the Stats Canada website that actually shows you in real time how the population changes. So the number here is 38 million, just over 38 million. Keeping this in mind, the real population is over 38 million, and my prediction population is just under 33 million. So this is lower than the current population actually is. Now, why might that be the case has a number of different reasons. For example, once again, this model only accounts for birth and death rates as contributing to the population. It does not account for immigration or emigration. It also took the birth and death rates of year 2000. And since then, the statistics have changed. For example, the birth rates have gone up and the death rates have gone down. Furthermore, modeling something 20 years in advance is a lot to ask for the actual same pattern to hold for that long. Exponential functions are really good at modeling on short time periods, but the further you get away from the data collection to the data prediction year, the worse your model will become, and this is something we have to keep in mind. Let's take a look at one last application of the course, and this is in some ways making the full circle back to the very first application we've seen on cells and cell size. So here we have a cubic cell, just so that we can easily imagine the actual shape. This is a little cube. Its side length is L, and its mass is M. What I would like to think about is, for example, how does this mass relate to volume? Well, an easy principle suggests that mass is volume times density. And I can assume that if a cell is really small, then the density is uniform. So the density is some constant d. The volume of the cube, of course, is length times height times width, so L cubed. So altogether, I have dL cubed as the mass. Okay, so my relationship here is mass is equal to density times the volume of the cube. Now, if the cell is to grow with time, then of course, while the density will not change and stay constant, the mass and the length will certainly change. So let's take a look at what it would mean to take a derivative of this entire equation with respect to time in the related rates type of manner. So on the left-hand side, I simply get the derivative of the mass. On the right-hand side, the density is a constant, so it will stay put. And then I have the derivative of L cubed. The outside function here is cube, so that will come down and the power will get reduced by 1. But the length itself is changing with respect to time as it's growing, so I have to multiply by the derivative of the inside, or dl by dt. So what I have here is a relationship between the rate of change of the mass of the function of the cell and the rate of change of the length of the cell. This is some kind of differential equation, but not concerning the exact same function, which is actually one of the issues. So let's see if we can rewrite the rate of change of the mass of the cell in another way so that we can equate the other two expressions for it. These two should be familiar with for you. It's from the beginning of the course. The cell ingests food at the rate proportional to the surface area. So the surface area of the cube is each of these little squares. There's going to be 6 of them, so it's proportional to 6L squared, or it's generally proportional to L squared, because proportional means with some kind of constant. And so we can say that the cell ingests food at some rate S times L squared. Okay, with the surface area. So my 6 for the number of faces got absorbed into this proportionality constant S. We also know that the cell consumes food at the rate proportional to the volume. So we can say that this is some constant V times the volume L cubed. Then, as at the very beginning of the course, we know that the rate of change of the mass is going to be affected by absorption positively. It absorbs food and therefore grows, and affected negatively by the consumption of the food that it actually needs to sustain life. What we have now is we know that the absorption is SL squared for some constant S, and the consumption is VL cubed for some constant V. Now, this is the second expression for the rate of change of mass, the first one being this one. Now, because both of these expressions describe the rate of change of mass, I can simply set them to be equal to each other and then see if I can derive another relationship out of that. Now here I can notice that I have gotten rid of the problem I had before, and now I have one equation that connects one function, specifically the length, and its derivative. I have eliminated the mass out of the equation, and so now I have a differential equation for the length of the cell, including the cell length and its derivative. So what that means is that I can take this expression and use this to solve for, let's say at the beginning, for dl by dt, in the hopes that I'm going to get an expression similar to y prime equals to ky when I am solving for the derivative of the function, and then be able to come up with a solution. Okay, so what do we have here? I'm going to isolate this term, and that means I'm going to divide both sides by d times 3l squared. So altogether, I'm going to have that dl by dt is equal to sl squared minus vl cubed all over d times 3l squared. Now notice that I have a bunch of terms that involve L, and in particular L squared. So what I can think of here is just splitting up these fractions across the bottom, kind of like undoing the common denominators. So what I'm going to have is SL squared over D times 3L squared minus VL cubed over D times 3L squared. I notice here that I can simply cancel out L squares and that will go away. Here, I can cancel out some of them, but not all. So what I'm going to have left is S over D times 3 minus V over D times 3 times L. Now, these constants are really bulky. So let me call this guy, let's say K1, and let me call this one, let's say K2, because these are just constants. This was the constant for the ingestion of the food. This was the density. The V was the constant for the consumption of the food, and once again, the density. So altogether, what I have now is a differential equation that looks like this. Some constant Ky minus some constant K2 times L. So my dl by dt is equal to this expression, K1 minus K2 times L. Well, unfortunately, this is not in the form y prime equals ky, because I don't have just the multiple of y, I also have a constant that is being added to this entire expression, which means that I cannot use my solution to y prime equals ky function to solve this equation. I'm going to need different tools. These different tools are the tools that we're going to develop in Math 118. So this is both wrapping up this course nicely and a really great preview into some of the things that we're going to look at in Math 18.